So in this video, we're going to be looking at lattice enthalpy as well as the factors that actually affect it itself as well. Now, lattice enthalpy is the enthalpy change for the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. And you can see I've got here an example for the lattice enthalpy of sodium chloride, which has a value of minus 787 kilojoules per mole itself. Now you can see, right, I'm forming 1 mole of solid sodium chloride itself from its ions it's made up of, which is going to be sodium ions and chloride ions in the gaseous state itself as well. Now, because this process, right, actually involves bond formation, where we're forming an ionic bond between the positive ions and the negative ions itself, right, we say lattice enthalpy is always going to be negative because it involves bond forming, which is an exothermic process which releases energy itself. Now, thinking back to module 3, we looked at bond enthalpies in terms of the average bond enthalpy, looking at a description for how strong a covalent bond is going to be. But in this case, we're going to use lattice enthalpies to talk about how strong ionic bonds are going to be, right? So yeah, if we look at lattice enthalpy, we can measure how strong an ionic bond is going to be. And we say, right, a large exothermic value for the lattice enthalpy. So a more negative value means that we've got very strong electrostatic forces of attraction. Remember the definition of ionic bonding: the strong electrostatic attraction between oppositely charged ions. So we're looking at these electrostatic forces of attraction itself. Now, if we've got stronger electrostatic forces of attraction between our oppositely charged ions, we will ultimately have a more stronger ionic bond. And before we move any further, let's look at what this actually means of having a more exothermic value for the lattice enthalpy itself. Now let's take two compounds itself, right? We've got XCl and we've got YCl, two ionic compounds. And let's see if the lattice enthalpy for these two ionic compounds is going to be as follows, where I've got minus 1000 kilojoules per mole for XCl and then minus 2000 kilojoules per mole for YCl itself. Now you can see the larger number is technically going to be the lattice enthalpy of XCl, which is minus 1000 because it's more positive, but because we're dealing with lattice enthalpies and they're all going to be negative, the more negative one is going to be the more exothermic one. So when we talk about lattice enthalpies, we normally say that this one is going to be more exothermic than this one. So in this case, YCl has a more exothermic lattice enthalpy compared to XCl itself. So moving on then, looking at the first factor that affects lattice enthalpy, that's going to be ionic radius itself, right? And what we can say is that smaller ions, they can pack more closely together, they've got a greater charge density, and so we've got stronger electrostatic forces of attraction itself. Now let's look at an example and let's compare, let's say, lithium ions with sodium ions itself in lithium chloride and sodium chloride, right? When we look at, let's say, lithium, right, we know that we've got two shells, right? So I've got one shell over here and then I've got my second shell over here as well. This is what I should end up with. And let's say if I were to look at, in this case, sodium ions, right? Sodium ions, they're going to have an extra shell itself, right? And so what I actually end up with is something that looks like this for sodium. Now, if I were to look at the number of shells, right, we can see that sodium, it's going to be just below lithium itself, and it's got one extra shell. If it's got an extra shell, the atomic radius is going to be bigger. But what about the ionic radius? Well, let's look at the electron structure of lithium and sodium. Lithium goes 2 and then 1 on the outer shell, because remember, it's an S block element in group 1, whereas sodium is going to have 2 to begin with, and then it's going to have 8 in the next one. And then it's also going to have 1 in the outer shell itself. Now let's say if we were to remove the outer electron, right, when we look at lithium and sodium itself, what we now end up with is not atoms, right, we now end up with ions itself. So I've got over here lithium, which is going to be positively charged, and then I've also got over here sodium, which is going to be positively charged. Now these are now going to be ions, so we can talk about ionic radius, not atomic radius, and we can see that sodium is going to have a larger ionic radius itself compared to lithium. Why? Because it's got more electron shells. And if, let's say, if I were to take away that empty shell there itself, you can still see sodium is going to have a larger ionic radius compared to lithium. Now the whole idea is the smaller your ions are actually going to be, the closer they can actually pack together, and so the greater the charge density they're going to have, and hence the stronger the electrostatic forces of attraction they're going to have. This would mean that something very small like lithium, right, if that was bonded to something like chlorine compared to sodium chloride, you know, because lithium ions are going to be smaller than sodium ions, they can pack more closely together, you've got greater charge density, stronger electrostatic forces of attraction between the oppositely charged ions, and hence you're going to have, and we're going to use this word now, a more exothermic lattice enthalpy. So as you go down the group, right, we know ionic radius increases, so the lattice enthalpy itself is going to become less exothermic itself as well. You know, ionic radius is going to be larger, right, every time you gain a shell itself. So the first factor that affects the lattice enthalpy is going to be ionic radius, but what about ionic charge itself, right? Now, the greater the ionic charge, the stronger the electrostatic forces of attraction is going to be to the ion itself. And so we know our lattice enthalpy is going to become more exothermic. You can see over here, I've got sodium plus ions, so I've got +1 charge attracting a -1 charge itself, which we can see over here. We've got a little electrostatic attraction. But then if I were to look at something like, let's say, magnesium 2+ in this case, for that to attract, right, a ion of chloride itself, where you can see we've still got a negative ion here, still got a negative ion here, the same negative ion. In fact, we know that the attraction between the +2 charge itself, the +2 ion itself, is going to be much greater compared to the +1 ion itself. And so I know, right, this electrostatic attraction over here is going to be stronger compared to that over here as well. So we can see the more positive the charge is going to be for positive ions, the stronger the electrostatic force of attraction is going to be, and so the greater the lattice enthalpy is going to be. What about, let's say, if I were to look at something like sulfide instead of chloride itself, and you can see here in sodium sulfide I've got a +1 ion itself, and that's going to be attracting this time a -2 ion of sulfur itself, and this attraction is going to be much greater compared to the one above over here with sodium chloride itself. So now that we've looked at our two factors that affect the lattice enthalpy itself, how would we actually explain this in an exam? Well, the first thing that I always recommend that you do is that you write out the actual ions that form the compound itself. Starting off with the first one, you could be asked to explain why sodium chloride or anything similar has a more exothermic, so in other words, a more negative value for the lattice enthalpy than cesium chloride itself. You look at sodium chloride, you've got sodium plus ions and you've got chloride ions. If you were to look at cesium chloride, you've got cesium plus ions, and then you've got chloride ions itself as well. You can see chloride stays the same, so we're not actually interested in that, but sodium ions is going to be different to cesium ions, not in terms of charge, but perhaps in terms of ionic radius itself. And when you look at it, cesium is going to be lower down, it's going to have more shells, and it's going to have a larger ionic radius itself. So here's what we need to say. We need to say that sodium ions are smaller than cesium ions itself. We need to say that sodium ions can therefore pack closer together and they'll have a greater charge density. And so sodium ions, they're going to have a stronger electrostatic force of attraction for chloride ions and hence stronger ionic bonds. Sodium chloride is therefore going to have a more exothermic lattice enthalpy. This bit is a key bit over here that a lot of people forget to mention. Just remember that. Look at the next one. We've got magnesium chloride versus sodium chloride. Why is magnesium chloride going to have a more exothermic lattice enthalpy than sodium chloride? Let's practice the metacognition again. You've got magnesium 2+ and chloride ions versus sodium plus and then chloride ions itself. Now, chloride itself, we're not actually interested in that, but instead what we're actually interested in is the difference between magnesium 2+ ions and sodium 1+ ions itself. And you can see magnesium 2+, that's going to have a greater charge itself. So in that case, it's going to form stronger ionic bonds itself, right? So how do we go about wording this? Well, we need to say that magnesium 2+ ions, they have a greater charge compared to sodium ions. Now, the next point, right, you don't have to mention it in this case, but I prefer to just chuck it in there anyway. Just because when you look at, let's say, say the ionic radius itself, going from left to right on the periodic table in this period, right, you know that your ionic radius is going to decrease. Why? Because you've got electrons in the same shell which can have similar shielding, and you also know, right, that the outer electrons themselves, they're going to be drawn in more because that positive nucleus is getting more positive and positive because the number of protons is increasing. So the nuclear charge is in itself actually increasing as well. So we can say magnesium 2+ ions, they pack closer together and they have a greater charge density. Magnesium 2+ ions, they are going to have stronger electrostatic forces of attraction for the chloride ions. Again, we need to be really specific about this part, like how we were in the last as well, mentioning what ions we're talking about all the time. Magnesium chloride, therefore, is going to have a more exothermic lattice enthalpy itself. Again, we need to get that point in there as well.